Okay, so this is the video corresponding to the one-way Anova code in our Markdown. And I'll just go through the code and just show you how where I've put things and how it works so that you can use it. And just as a reminder, make sure that you download the code and the associated data file before you go through this if you want to follow along. So here is our studio. And what you'll notice here is that this is an example of a one-way Anova. And just as a reminder, you'll need to change your working directory. And starting right here at line 13, like so, and you will need these particular libraries installed. The one that might be a little different from the other videos is this one car, which just makes calculating something slightly easier. So let's talk about the type of question this can answer. So here I've made up a example question where the Society for Personality and Social Psych has gotten this feedback that students really think that their grant applications are scored more poorly than non-students. So the idea here is that, you know, if you're an undergraduate or graduate, maybe you get worse scores than if you're already have your doctorate, postdoc, or faculty. So here, if we wanted to answer this question, we might take a random independent sample of 200 grant applications from 4 different groups. So undergrads, graduates, postdocs, and faculty. And then we're going to look and see if there's a difference in the dependent variable of examined grant scores, which in this example can range from 0 to 100. So we're going to use a one-way ANOVA to do this because we have one independent variable, the level of training that somebody's received, and we have 4 levels of that independent variable: undergrad, graduate students, postdoctoral fellows, and faculty. So since we have 4 levels and we have 1 independent variable, we'll use a one-way ANOVA. Just note that the data file that corresponds to this is this one.way.anova underscore data.csv. Okay. So let's do this code here. So first thing that we're going to want to do, and remember, you can hit Control Enter, Command Enter to run just a single line. First thing that I'm going to do is just bring the data in and calculate descriptive statistics. So here I'm going to read the data. You'll notice that now over here I have 800 observations, group and score. That's 4 sets of 200 observations. And what we're going to do first is we're just going to calculate some descriptive statistics. So here, starting in line 36, I'm going to say, look, to calculate all the means, take the data, group it by the group, and then summarize the variables and for what. Okay, so this code right here says take the data and then put it into, or pipe it into, this thing called group by. So that's what groups we want, and we called those groups. So this is just going to put it into our 4 levels. And that lastly, we're going to summarize the variable score by the average. Okay. So here we are putting our data variable, our independent variable, our dependent variable, and then the type of summary we want. And we're going to do that for standard deviation as well. So let's go ahead and do that. So I'm just going to hit Control Enter and Control Enter again. And just to show you what these look like. So if we go over here, I'll just go down here and we'll just spit out what these look like. So here we have all all dot stats means. And this gives us the average for faculty, graduate, postdoc, and undergraduate students just in a tibble from tidyverse. And we can do the same thing for standard deviations, and we get the standard deviations. And why do we do this? Because we want means and we need standard error of the mean to graph later. So we're always going to do our descriptive statistics first. The next thing that I did here, starting on line 45, is to calculate the standard error of the mean. So here, I'm going to do this for each cell, so faculty, graduate, postdocs, and undergrads. And I'm going to take the standard deviation that I just calculated above and put that number in here. So I'm saying, look into the variable all standard deviations, look inside of that, or I'm sorry, yeah, look inside of that and tell me the name of the variable. Notice this stdev right here is the same as this. So if I were to have changed that to something different, like standard or whatever, we just have to put that there. And then I want the first value of that, the second value of that, the third value of that, using this little number here. And we know that there's 200 observations of each because we already have been told that. Okay, so we're just going to simply calculate each one of those. And then this last line here, and let's see if we can do this cool arrow looking thing. Yeah, look at that, neat. This last line here is just putting them all together. So remember that we can use this, this C function to combine things. And so we'll just go ahead and do that as well. And now if we wanted to just sort of like look and see what that looked like, we could type in all of the standard errors of mean, we just get a list of those. Okay, so now we have our descriptive statistics, great. What we need to do next is check the assumption that the variance is equal using this thing called Levine's test. You can, if this, so here we're going to test the null that the groups are the same. So the variance in the groups are the same. So really we want a non-significant result here. This is just like the the equality of variances in the Shapiro-Wilk test, or the normality assumption rather. And so just so you know, I didn't write code for this, but if you had a unbalanced design where you didn't have equal groups or unequal variance, you could use this thing called one-way.test in place of the AOV function, then you would get basically the same thing. Okay, so there's both there, but in this case, we have a balanced design, 200 in each cell. So we're going to go ahead and run this. And here we just use the Levine's test. And remember, we want dv as a function of IV for what data? Question mark. And so here we have Levine's test score group data. And so let's run that. And we'll see down here that this p-value right there is greater than 0.05. So we're good to go. So now let's conduct the test. Here, super easy code, right? We're going to call this results again. We're going to do this AOV function and then dv squiggly line IV for what data. So here we want to know, what are the scores? Do they differ by a function of group? And so if we run that, we'll get a list of things. This test is a little bit different than some of the t-tests where it's not as easy to just jump in, excuse me, to the results. So we're just going to use the summary results function so that we can see down here the values that we care about, just how to read this. Here's our degrees of freedom for our group. Here's our degree of freedom for our residuals or our leftover degrees of freedom. Here is our F value, our obtained F value, and here's our P value. So this really means this is 2 times 10 to the negative 16th, which is essentially really, really, really little, right? We could also look at these little asterisks. Those tell us what level of the significance it's at. So here it says 0, but I usually like 0.0001. I don't like saying p equals 0 because it doesn't. Just equals something really small. Okay, so here we have a significant result. One thing we don't know yet, though, is we don't know how these things differ, right? And we don't know how big this effect is. So let's go back here and try to determine how big the effect is. So we can do this with an eta squared, and we'll just go ahead and use this function called eta squared. And I like calling it a particular variable name, so we can go back and call it later. So I'll hit Control Enter, and then I'll hit Control Enter again. And here you'll see that we have an eta squared and a partial eta squared. They're the same because we're using a one-way ANOVA, but this is our effect size, this 0.0 or 0.308, blah, blah, blah. Okay. Now, what we don't know is we don't know which ones differ as a function of each other. So we need to do these post hoc tests, right? And remember that when we do a post hoc test for a one-way ANOVA, what we're going to do is we're going to do a bunch of pairwise t-tests. But we can't just do regular t-tests. We have to adjust the p-value a little bit because we're doing a lot of tests, and that increases our potential for error. So we're going to use this function called post hoc pairwise t. And we're going to say, okay, well, what is the thing that we're testing? It's the results. So we really want to remember that what we put in there is not our data, but instead the results of our ANOVA. So this results comes right down here. And then this p-adjust method is the way of adjusting our alpha value. And so we're going to use the Holm correction because that one is pretty good. There are other ways to do that if you want to, but for now that's fine. So let's come down here and we'll do this post hoc test, and then let's display it. And here what we get is we get comparisons between each of the levels of the independent variable, and the number that's in here, these are p-values. So it doesn't tell us mean, standard deviations, anything. It just tells us which ones are different from each other. So here we want to look at each one of these and see if they're less than 0.05, right? So let's do that, and we'll just put a little dot by them. So this one less than 0.05, this one, this one, this one, and that one. So pretty much all of them except the comparison of undergrad to grad. Okay, so when we write this up, often what I will do is I will try to summarize these in the simplest way possible. So you'll see in my example here, I say that the only thing that wasn't significant in the post hoc test was this particular one right here. And I do that simply because I think it's easier to say that than 1, 2, 3, 4, 5 different comparisons. So there's a little bit of leeway in how you describe these things. Okay, so now we have all of the information. Let me just go ahead and run this entire thing through so it shows us everything. And now we're just going to write it up. So here we're going to say, all right, a one-way ANOVA was conducted to determine if there's a difference across the levels, and we'll name those on grant score. So I've said the IV and the DV. And results indicate a significant difference across all the groups. And I'm going to put our F value in, our P value in, and our eta squared value in here. The way that I've done this, I've just simply typed those values in because that was a little bit easier, except for the effect size I put in R code. I wanted to show you a slightly different way of doing this because it's not wrong necessarily to put those values in. It's just sometimes a little bit easier to call the code. So you could probably edit this to do that, but I wanted to show you different ways. And then again, notice I said pairwise contrasts that indicated significant differences between faculty compared to graduate, postdocs, undergrads. So I put all of those in there. And then scores also differ between postdocs compared to graduates and undergraduates, and all postdoc tests use this home adjustment. So despite what I had just said, I wrote all of those things in there anyway. Little bit up to you. So we want to remember in your written results, convey the correct information, but other than that, there is a little bit of leeway there. Now we need a figure. So in our figure here, what we're going to do is the same thing that we've done before. We need a group, we need the averages for those groups, and then we need the standard error of the mean for the error bar. So this is our labels for X. These are our values for Y, and these down here are our error bars. Okay, so we're going to do this for all of our plots. So this should be pretty familiar to you if you've watched the other ones by now. And all I'm going to do is I'm going to say, well, look, for group, put together faculty, graduate, undergrad. Okay, and I'm just going to call them those names. I'm going to remember to put those in the same order that was in my tipple. So if I come down here, just as a reminder, I might say all.sems, or I'm sorry, all.means, and it has faculty, grad, postdoc, undergrad. So it's going to put them in that order. So we want to just make sure that we put them faculty, grad, postdoc, undergrad right here in the same order. Okay, so great. Let's run that. That gives us all the information to put into a plot. And then this plot looks very, very similar to before. We're going to say, take this entire data frame and plot it. It's got a lot of stuff in there, but we already put that stuff in. For our X variable, for our bar graph, for X, we want group. For Y, we want the mean. Remember, identity just means that we're going to use a bar graph here, and we're going to make them gray because we're trying to do APA. Then for our error bars, we want X group, and then we're going to use the means and the standard errors of the means to go up and down. Another thing that sometimes throws people off is you always need this little plus sign at the end when you're adding different elements to ggplot. So if you get an error or something like that, it might, sometimes it's that just as a troubleshooter. And then again here, this whole area is basically just making everything grayscale. If you wanted to change these so that they were prettier, you could keep the panel this side of the equation and change this side of the equation. But we'll just leave those right now. And if we were to do that, we'll get this pretty close to APA style graph here. And also remember that you want to have your figure name and your note down here at the bottom just to make that AP as well, APA. So let's knit this, Control-Shift-K or Command-Shift-K. Oops. I have my wrong working directory in here, so let's fix that and do that again. And what we'll see is that when this knits into an HTML document, we have this really pretty write-up where I've kept the output in here for now, just so you can see it. But again, you can hide this as much as you want. We have all of our relevant information. Then we have our written results. Notice these are nicely APA formatted with italics and everything in the right place. And then we have our figure with a note and sort of a title up here. Okay, so this concludes the one-way Anova with post hocs and figures and a write-up. As a reminder, just make sure that you can use this code on your own, because sometimes you get little errors when you are trying to put things on your own computer versus watching someone else do it. And as always, if you are interested in learning more, have questions, I am always around to help.